Okay, so to do the rectangular approximation method, you're going to follow these steps. So step 1, divide or partition the interval into however many subintervals the question asks for. It usually directs you specifically with how many either subintervals or rectangles it requires. Step 2, create those rectangles whose base equals that given width that would come as a result of dividing the total change by the number of n subintervals, and then times the height, which will be determined by either using the left endpoint, the midpoint, or the right endpoint of the subinterval. And then you add up all these areas together. So this makes it sound kind of complex. You're literally drawing in number of rectangles and multiplying base times height and adding them together. So it's not actually that bad. So what you're going to be practicing in this video is knowing the different approaches, right versus left versus midpoint. So it says illustrate the use of the right and the left endpoint rectangular approximation methods on the graphs below. And here it tells us to use 5 rectangles. Okay, so that's basically what step number 1 is telling you to look for. So now we know we're going to split it into 5 rectangles. It does not say that they have to be of equal widths. Often that's something we look for, but it doesn't state that. So we can actually make these rectangles whatever width we would like. What it is not flexible about is it wants us to use the right hand or the right endpoint approach first and then the left endpoint here. These are the same exact graphs, so we're going to see how those cause any differences in our areas. So to use the right rectangular approximation method, it means we're going to start the height of our rectangles on the right and then make the rest of the shape based on that. So again, you go to that next point and make that the right part of your rectangle. And you're just going to continue doing that. Whether it's over or under isn't your concern. You're basing it all off of the height of the right endpoint of the rectangle. Perfect. And so once you've actually sketched in these rectangles, you're going to go through and then add up the area of the rectangle, whether it's over or under. Again, you just get to ignore here. So this first one is 2 by 3, so that's simply going to be 6. And then again, 1 by 1, 1 by 5, and then 2 by 5. So the right endpoint rectangular approximation method is going to equal 6 plus 1 plus 5 plus 10, which is an area of 28. So now we're going to look at the same points, but this time when drawing my rectangle between each pair, instead of using the right hand point of the rectangle, I'm going to use the left end point. Okay, so in this case, we're going to start our rectangle here on the left and draw that height. And again, and again. And you just continue basing it off of the left endpoint of each pair of points that you're looking at. Okay. I find the left one harder to draw personally because it's like I don't know where it's going to, if that makes sense, but it's really still not very difficult. So we're going to have an area of 4, 6, 3, 1, and 10. Which gives us a total area of 24. And you can see visually how this would come to be, right? That this one has a lot more extra area above the curve, whereas this one, for the most part, minus this one rectangle in the middle, was an underestimate. Alright, so in example 4, it says use 4 rectangles to approximate the area under the graph of y equals x squared minus 2x plus 2 from x equals 1 to x equals 3. We're going to use all 3 approaches this time. And I'm going to instruct you to make these rectangles of equal width because in general that's the direction we're headed with this, just because the more uniform things are in math, the easier it is for us to generalize it. So the 4 rectangles is important and the interval on which we're looking at. So we're going from 1 to 3 and turning it into 4 rectangles. So if we're thinking about how wide we want to draw these rectangles, right? We need to think of the fact that it's from 1 to 3, which is 2, a change of 2, and we want to divide it evenly into 4 rectangles. So that means that the width of each rectangle is going to be 1/2 or 0.5. So often what I'll do is I'll at least mark this at the bottom of the graph, since I don't know how tall I'm going to make them until I decide which method I'm doing. If I at least mark out these beginning and ends of the width of each rectangle, it gives my brain a little more structure. So for the first one, they want us to use the left rectangular approximation method. So I'm going to start at the leftmost point and draw my rectangle over until it reaches that second point. Okay. And then again, I'm basing the height off of the function value on the left side of the rectangle. Okay, and then for the next one, that's going to be up here. And then all the way up here. And that is my 4th rectangle. So before I go calculate the area, I'm trying to figure out the heights each of these got to for the base times height part. The first one's easy. It went all the way up to 1. This one, it looks like it went up to 1.25, 2, and then maybe 2.25, or not 2, 3.25 as the heights. And then I know each of the bases are 1/2, or in this case, you know what, let's be consistent. I'm going to write 0.5. So each of these bases is the same width because I set it up that way. So to find this left rectangular approximation, my base of my rectangle is 0.5 and the height is 1 for the first rectangle. Then I have a base of 0.5 again times a height of 1.25. And I think you guys have a table on your notes for these calculations. Then again, same base, and then the height of this one would be 2. And then same base times a height of 3.25. And you would just use your calculator. In this case, they're kind of grosser, but they're not too bad. And you're going to get a total area of 3.75. Awesome. Now let's do the same thing for the right. Again, I like to go ahead and mark off the width. But this time I'm going to start at the rightmost given point to draw the rectangle height from, wherever that is. Then the rightmost, and then the very top. So this one's definitely going to be a larger area because all of these are over the curve versus under. So this one I think went up to 1.25 to 3.25. So it has the same last 3 as its first 3, and then it has one more that's much larger versus the first one we had over here, which was 1. And so that's a height of 5. So then for the right rectangular approximation, we're going to get 0.5 again as the base, since it's always the same no matter which method we use there. What changes is the height. So 1.25 is our first one in this case, and then 2, and then 3.25. And then obviously the big difference, instead of a 1 as the first, we have a 5 for the last. And so this is going to give us a total area of 5.75 with that difference. Okay, so we haven't done one of the midpoint yet, so this will be your first example with it. And as you have already kind of seen, it's definitely more accurate than just the left or the right because it takes both into consideration, but it is much more of a pain because we can't use these beginning and end cuts for our rectangles to plug in for our height. We have to use what's in the middle of them, right? So for this first one, for instance, we have to use what's in the middle of 1 and 1.5, which would be whatever the height is at 1.25, which off the top of my head, I cannot exactly tell what that is. So this is where you would really have to use your calculator, type this in y1, and actually get the function output for 1.25 as the input for figuring out basically the height of that rectangle there. Then the midway point between 1.5 and 2 is 1.75. So that would be what we would base this height on, which again is not looking pretty. And then the midpoint of this next one would be 2.25. I'm not doing very good drawing these. And then the last one, of course, would be 2.75. So I would actually have to use my calculator for these to type them in and verify they're what my eyes are looking like they are. So the way I would write this on my paper is I have 0.5 times f of 1.25 and then plus 0.5 times whatever f of 1.75 is. Again, it's just going to be in a pretty gross decimal from your calculator, plus 0.5 of 2.25 and 2.75. And if we do all of this in our calculator, it's actually going to come out to be 4.625, which is, if we look back, not forward. If we look back at our first two, right, we think of this as being the most accurate because it should fall somewhere between this over and under estimate, and we had a 3.75 and a 5.75, and this falls nicely between them.